Lara and Laszlo mentioned that we are a bio-nanocomposite group, so we represent that part in the project. This is the structure of my talk. After short introduction, I would like to show you our achievements, just highlights, because we are lucky that three of our colleagues are here and they will tell you more details in the future about the achievements. I just show a couple of slides about this, what we reached. So these results belong strongly to the project. This was our aim to do. And there are also some side projects that grown during the work, which are, to say, some auxiliary project for us. Also, I tell something about future challenges, because I am the leader of this project component. I would like to tell something about statistics, what we have bought, and what are about the public relations and so on. So this is a building that Clara already showed. Here is our place, this floor. This environment is very encouraging environment, because physicist people, chemist people are around, so we have a possibility to do collaborations and a lot of discussions. And there is, in this photo, I used to tell that this is also a very lucky situation, because we are close to the place where light comes from. So the light comes from the chemistry department. If you did not know, that's a proof for that. So we are working on a reaction center protein. I used to tell that there are many respected scientists who don't believe that biological proteins can be good for practical applications. But there are many proofs that they can be used in practical applications. But we are in a very lucky situation, because I don't think that I have to express that photosynthetic reaction center protein is very important in nature. Laszlo already said that this is the protein that can convert the light, even the energy of a single photon to chemical energy. So the quantum yield of the conversion is practically 100%, okay, 98, but it's very close to 100. But we are in a very lucky situation. We have this protein in our hand. We can isolate it, we can purify that, and we can do with this protein whatever we want. We can see that, we can lift it up, we can put to other place, we can cut it. So I think if somebody doesn't believe that this is useful for practical application, this is really challenging that we have this protein in our hand. And this protein has, this is a protein, has some protein part built in with amino acids, and also there are cofactors, and these cofactors assure the electron transport chain within the protein. This protein has so many good properties that can be used for practical application. One is that it has a specific absorption spectrum. It has a very specific in the near infrared, and near infrared is a good range in the absorption spectrum. These are the kinetic components of the electron transport, and there are kinetic components from femtoseconds to seconds, and these can be engineered. So we can create a protein with the kinetic components, any kinetic components what you want. If you tell me that you want a protein that creates a charge pair in 1 millisecond, I will do that for you. If you want a protein with nanoseconds, I will prepare you a protein with a nanosecond lifetime. The other one we already mentioned, that the quantum yield of the charge separation is 100%, and that's a very interesting, and it's not worked out well. That there is a redox interaction with the environment, so we have an electron with excess energy, and this energy can be used for something, for wiring out in an electrical circuit, or you can use this work in chemical reactions, for example, reducing a component, for example, around the reaction center. So there are many advantageous properties of this protein. So how we started, the start was not without background. Before the call, before we wrote the proposal, we already had a good result. Once we are experienced with the reaction center protein, we have a long experience with that, and also we wrote a paper in 2006 that this was the preliminary result. Laszlo mentioned that the competition is huge in this field. I remember the story of this paper. One of the reviewers asked me why we don't refer that and that publication, and I looked in the net, what is that publication that the reviewer wanted us? And I found that publication in a web preliminary result. Mm-hmm. But this was not a real publication. This was not in the real printed issue. It was just on the web. At that moment, the reviewer wanted that to publish. So the competition is really huge. And this was our first structural proof that the reaction center is bound to the carbon nanotube, this image in a color version. And also it functions. It keeps the function. After light excitation, it creates, this is an absorption change. The absorption change is a good tool to monitor the electron transfer within the protein. So it really works, and it is really stable on the carbon nanotube. It keeps the stability until about 3 months. So our aim was, this is a citation from the project document. Our aim was we subdivided our aim to 2 parts. The first 2 years was to prepare reaction center protein from different species, from different bacterial species, to find what is the optimum, what is the best type of protein to bind to carbon nanotubes, and to find the best carrier matrices, what is the best method to bind the reaction center, to functionalize or unfunctionalized, what kind of functionalization we can use. And the second 2 years, we wanted to see possible practical application. Laszlo said that this is still basic research, but strongly innovation-oriented, because I think that this research can show some possible directions of possible practical applications for photovoltaics or any other optoelectronic applications, because we have an electron with work, I mean with excess energy. So this, okay. Okay, now in the next part I would like to show you a couple of highlights from our achievements. So first we wanted to find out what is a good binding strategy to bind the reaction center. We tried several strategies. One was the classical physical absorption. This was the first experiment, just physical absorption. This also works because the reaction center is a membrane protein. It is highly hydrophobic. These are the hydrophobic parts, and the carbon nanotube is hydrophobic. So if we just let the thermodynamics work, the thermodynamics itself will do what they have to do, as the hydrophobic interaction makes possible for the reaction center to bind the carbon nanotubes. And also, but the reviewers also asked us that what is the orientation, what is the structure, and what would be the best orientation for the reaction center protein. And also we wanted to see that And we tried several specific orientations, specific binding to different functional groups. These are still not specific because there are many amine and carboxyl groups on the protein, and we bound the protein to carboxyl and amine groups, but we also tried specifically engineered proteins with his tag to bind the carbon nanotubes. There are many, these are just examples because we did so many EM and AFM images to prove that the reaction center is there. And also spectroscopy. Spectroscopy is an obvious tool to investigate the photochemical reaction of the reaction center because there are redox-active cofactors in the protein, and these are chromophores, so the redox state of the chromophores can be monitored by the spectroscopy. Steady state and kinetic absorption spectroscopy. Also, the stability in another issue. I already said that something like 3 months is crucial. Actually, we had a sample that was active even after 1 year. So that was an interesting story that we wanted to clean our fridge, and we wanted to select the samples, what samples we have and what is not necessary, let's throw it away. And before throwing it away, we checked the samples, and interestingly there was one sample that showed a little activity, not huge, 10–15% of activity. And it was just a code, and one of our students did this sample, and we called Hajnalka Füvesi, who did this sample. Tell us what was the date when you prepared that sample, and it was exactly 1 year ago. So the same day, just 1 year before. So it was still active after 10–15% activity. But the typical is you see that the activity drops after 3 months. Suddenly, Melinda will tell details about this project. So optical spectroscopy is a useful tool to characterize the electron transfer, but of course it has some limitation, because if we are characterizing small chromophore concentrations, for example in layer structures, optical spectroscopy cannot give good resolution or sensitivity. This is one thing. The other thing is that we would like to see photocurrents, and we would like to see electric properties of the samples. So we set conditions for measuring electric conditions. And this is an example that actually there was a problem how to contact on the sample, on the carbon nanotube samples, and there was one possibility to deposit the sample on the surface of the ITO, because it is very good. For the ITO, you can make good contacts. And this is our first experiments with the ITO. Here is the reaction center on the surface of the ITO. The AFM image shows that the height coincides with the size of the reaction center, and this system responds to the light, and this response is concentration dependent. Tibor will tell more details. And the other direction is to measure photocurrent in electrochemical cell. We designed an electrochemical cell with a classical 3-electrode arrangement, and it was connected to a potential state, and the working electrode is a specific sample. And so the working electrode is a sample deposited or bound to the ITO. With the ITO, we could make a good contact, and we measured photocurrents under different conditions. Tibor Sabo is professional in this. He designed the electrochemical cell, and he will tell you details about that. I just would like to show the highlight that we can measure photocurrent in this system, and this photocurrent responds to specific treatments which are characteristic to the reaction center protein. The other direction is, and it is still challenging, to try to measure photocurrent in dried samples. Because in this sample we have an electrochemical cell, the electrode immersed in electrolyte solution, and if we illuminate it, you can measure current. But it would be very challenging to measure currents in dried samples. We try to use the classical dye-sensitized solar cell model, that in a multi-layer structure, instead of dye, we use the reaction center protein as a sensitizer. And in this system, we can measure these characteristics. I think Tibor can also tell about this more detail. At the moment, I admit that I don't know what is the better directions, because we have to learn how to do the layer structure, and so we put the reaction center in this layer with the carbon nanotube. We don't have these nice characteristics all the time, but we have good improvement, because in our first experiments, for example, out of 10 samples, there were only 2 working samples. Now we can do the sample with a very good yield. Out of 10, 8, 9 is working. Now the question is, what is the reproducibility of the photocurrent? So that's the direction. The other direction of our work is to try to bind the reaction center to bundles, now carbon nanotube bundle structures. We don't have instrumentation to measure photocurrent on single carbon nanotubes. Of course, if we want, we can do it, but this is not routine in our lab. But we can measure the photocurrent of reaction center carbon nanotube bundle structures routinely. So that's why we turned to this field, and we bound the reaction center to these bond structures, and we can measure photocurrent in this system. And there are some other projects which at the beginning did not belong strongly to the project, but it turned out during our works that this is important to work on this. One is that the reaction center produces singlet oxygen when it is excited by excess light, and singlet oxygen is a harmful subject because it oxidizes the protein itself also, so it is very important to characterize what is the equilibrium concentration of singlet oxygen in our sample, and we started to work in this project. It started with Katohaidu, but Katohaidu is in Greece at this moment, and Aniko Kinka continues her work, and we will give Aniko is here. She will give a complete lecture tomorrow about this topic. The other connect, if we have experience with a photosynthetic reaction center, it would be interesting to try other redox active proteins with carbon nanotubes. Redox active proteins are very important also in medical applications, for example. One of these proteins is peroxidase, and hydrogen peroxide is very important in medicine, and we tried also the peroxidase activity. This is we try to create a biosensor for hydrogen peroxide, so measuring the hydrogen peroxide concentration. Another material is the porous silicon. We bound the reaction center to porous silicon. Also, it is So there's a proof that the reaction center is bound to porosilicon and the photosynthetic activity, it shows photosynthetic activity. So in summary, I can state that we bound reaction center to carbon nanotubes with different type of carbon nanotubes from different reaction center protein and different methods were worked out. The successful binding was proved by structural and functional investigations, and the reaction center showed activity after the binding, and it was stable for a long time. Electron chemical cell showed that photocurrent. So a sandwich structure was created for optoelectronic applications, and there were some auxiliary projects. So the future challenges, there are a lot of future challenges. The efficiency, what are the conformation in the system. Another electrodes we have tried. Clara already shows our publications. What we have bought, we built the systems to measure the electronic properties of of our samples. We are very proud of our awards. These awards were there during the project. There are a lot of cooperations, ongoing cooperations. Group members, thanks everybody who were involved. Public relations, Clara already mentioned. Of course, we enjoy the social life.